Hello everyone, this is Professor Roman. Let's continue the ring theory lectures. So far we have discovered the following relationships between the algebraic structures we've been studying. A Euclidean domain is a principal ideal domain, which in turn is a unique factorization domain, which is of course a factorization domain, and by definition is an integral domain. However, none of the converse implications holds. In example 4.9, we saw that an integral domain need not be a factorization domain. In example 4.6, we showed that a factorization domain need not be a unique factorization domain. And it can be shown that if R is a unique factorization domain, then so is R square bracket x. And I'll leave that for you to ponder. And since the integers form a unique factorization domain, so is C square bracket x. But we did see in an earlier example that this is not a principal ideal domain. So that takes care of the converse implications for these three. They do not hold. This one's a little trickier. Principal ideal domain does not have to be a Euclidean domain, and we're going to go through that now. I haven't seen a detailed explanation of this in textbooks, a counterexample with all the details. In textbooks, there are a couple of papers that I've seen, one in the American Mathematical Monthly, one in Mathematics Magazine. I give the references in the book. At the end of the book, there's a reference section, so you can look those papers up if you want to. But here is a detailed explanation. This integral domain, which for want of better notation I'll call R19, is not a Euclidean domain. And this is going to be the easier part of the explanation. We have to show that that it is a principal ideal domain. That's going to be a little trickier. So, as to why this is not a Euclidean domain, we can use universal side divisors. Because Theorem 519 tells us that in a Euclidean domain, any non-zero, non-unit with minimum norm among the non-zero non-units is a universal side divisor. So our goal is to search for those elements and show they are in fact not universal side divisors. So let's let theta denote this this complex number here, and define the norm in the usual way. It's the square of the complex norm. And we want to first find the units, which is similar to something we've done in an earlier example, so I'll leave it for you. Those are positive and negative 1. As far as the elements of minimum norm among the non-zero non-units, if this is the norm of A plus B theta, an arbitrary element of R19, it can be written this way. Now, if B is not 0, then this norm is at least 19/4. But if B is 0, then the norm is just A squared, and so if A is positive or negative 2, we get a norm of 4. That will be the smallest norm among the non-zero non-units when A is positive or negative 2. So according to that theorem I just mentioned, 2, for example, is a universal side divisor. And so if we divide theta, this expression here, by 2, use the Euclidean algorithm, the division algorithm, we get this, where r is either 0 or a unit, positive, negative 1. But if we move the r to the other side, we have theta minus r. 2 does not divide theta minus r, regardless of which value r takes, whether it's 0 or positive, negative 1, because when we look at the imaginary parts, we get b equals 1/2, but b has to be an integer. Okay, so 2 is not a universal side divisor, therefore R19 is not a Euclidean domain. To show that R19 is a principal ideal domain is going to require some work, and it begins with the following definition. An integral domain R is almost Euclidean if there's a function delta from the ring to the natural numbers, this is from all elements of the ring, 0 included, for which the following hold. Delta is positive definite, so this should be delta here. Delta of A is greater than or equal to 0 and equal to 0 if and only if A is 0. For all elements A, B, and R with B not 0, we have this inequality, which is the same condition we encountered in the definition of Euclidean domain. And in place of the division algorithm, we have for all A and B and R with A not 0, either A divides B or there exist elements X and Y and R for which these inequalities hold. Okay. If this obtains, we're going to say that R delta is an almost Euclidean pair. Now, the virtue of almost Euclidean domains for us is this theorem. An integral domain R is a principal ideal domain if and only if it is almost Euclidean. So almost Euclidean is a characterization of principal ideal domains that never mentions the word ideal. As to the proof, suppose first that R delta is an almost Euclidean pair. If R is a field, then it's also a principal ideal domain. So we can assume R is not a field. Let I be a non-zero ideal of R, and let A, B, and I have minimum delta norm among all the non-zero elements of I. Then for any element of the ideal, B in I, the choice of A implies that this inequality this set of inequalities cannot hold, because delta A is minimum among the non-zero elements in I. This is in I because A and B are in I. And so for this to be a strict inequality, AX plus BY has to be 0. But then this inequality, being strict, would be violated. So there's no room for this. Therefore, we have to have the alternative, A divides B. B was an arbitrary element of the ideal, so A generates the ideal. And therefore the ideal is principal, and R is a principal ideal domain. For the converse, suppose R is a principal ideal domain. Then, of course, it's a unique factorization domain, so we can define a function, which will be our almost Euclidean norm, as follows. Delta maps R to N. Delta of 0 is 0. We need positive definiteness. And for any non-zero element A in R, we can write A as a product of irreducible elements with possibly a unit factor. Doesn't matter. The factors xk then are irreducible, not necessarily distinct. I wrote that here, even though, strictly speaking, I didn't need to, because if I left that out, if you assume these had to be distinct, you'd be making an unwarranted assumption. But I put it in for clarity. We set delta A to be 2 to the n, where n is the number of irreducible factors. To see that R delta is an almost Euclidean pair, it's quite clear that parts 1 and 2 of the definition hold, and I'll let you ponder that. As to part 3, suppose that A and B are in R with A not 0. Okay. We need to produce x and y for which this holds. And we can assume, or we need to show that A divides B. So if we assume A does not divide B, then we need to show these inequalities hold. So consider this ideal generated by A and B. Everything in there is a linear combination over R of A and B. And since we have a principal ideal domain, we can assume this is generated by an element C. So there is an alpha in R for which A equals alpha C. But B is not in the ideal generated by A, and so this ideal is properly contained in I, which means that alpha cannot be a unit. So C properly divides A, and that implies that delta C is strictly less than delta A. But there must exist x and y in R for which C is ax plus by, because C belongs to this ideal. So we have the inequalities that we're looking for, and that completes the proof. Okay, so now we are ready for the main step. The pair R19 delta, where delta is the usual norm, the square of the complex norm, is almost Euclidean, and therefore it is a principal ideal domain. So again, I'm going to leave parts 1 and 2 of the definition of almost Euclidean pair to you to sort out. And we'll get right to the core part. Suppose that A and B are in R19, A is not 0, and A does not divide B. So we need to show this. B is also not 0 then, because otherwise A would divide B. The first step, now let me just mention that, there may be other proofs of this that I'm not aware of. So this first step, for example, may seem a little strange, but this is typical of the proofs that I've seen. So you might be able to do the entire argument using this set of inequalities rather than this set. But it seems convenient to divide this through by delta A to get something that looks like this. And it's not necessarily clear right now why that's convenient. But it does raise an issue. Because A does not divide B, the element B over A does not belong to R19. And so the first thing we should try to do is get a handle on where b over a does belong. It's certainly a complex number, but that's not very specific, and we can do much better than that. So for convenience, I'm going to denote x plus y b over a by alpha and square root negative 19 by beta. And also z prime is the set which consists of all the integers and all the half integers. So R19 is z plus z prime 1 plus beta. That's what this is. Here's the z prime because you have z over 2. This is contained, strictly contained, in z prime plus z prime beta, which in turn is strictly contained in q plus q beta, which is strictly contained in the complex numbers. And I'll let you ponder any issues there. So we can say that every element of R19 has this form x plus y beta, where x and y are in z prime. And that since q plus q beta is a field, b over a lies in q plus q beta. Now don't read anything into here I didn't say. Every element of R19 has this form. Not every element of this form belongs to R19, because this is a strict inclusion, and that's okay. So there exist integers, c, d, e, and f, for which b over a is c over d, a rational number, plus e over f beta. Combine this under a common denominator, and after canceling any common factors among df, cf, and de, we get b over a has the form u plus v beta over w, where u, v, and w are relatively prime integers. And that's critical. We can further assume that w is positive, as we can move any negative signs to the top. And also b, a does not divide b. This should be since. That means that w is at least 2. Because if w was 1, a would divide b. So in summary then, alpha, which is x plus y b over a, now looks like this. The integers u, v, and w are relatively prime. W is bigger than or equal to 2. Now, to examine alpha more closely, we have some options. And it's going to turn out that we're going to need more than one option. But the first thing that might occur to you is, let's just write x as what it might be, x1 plus x2 beta, and y is y1 plus y2 beta, where the xi's and the yi's are in z prime, and just compute this. Okay. So that's what the computation looks like. And now we're depressed, because this looks terrible. But if you stare at it for a few moments, you may see something quite surprising. Take a look at this coefficient of beta. It is a linear combination of w, v, and u. Coefficients are x2, y1, and y2 are members of z prime. Now remember, we get to choose x and y. We're searching for x and y that fits those two inequalities we need. So it's up to us to find them, to choose them. Well, W, V, and U are relatively prime. Whenever you hear those words, the next thought in your head should be Bezo's identity. Because these are relatively prime, there exist integers, x2 prime, y1 prime, y2 prime, for which this expression, this coefficient, is 1. So we'll pick x2 to be x2 prime, y1 to be y1 prime, and y2 to be y2 prime. And we have now alpha equals x1 plus 1 over w times this here. Okay. This tells us one thing right away, and that is alpha is not 0. Our choice that we've made so far of x2, y1, and y2 guarantees alpha is not 0, which means that one part of the inequalities that we're trying to show, this one here, is valid. Okay, because alpha is not 0. Okay. But we can do better. Still don't like this. But we're trying to divide it by w. So it is time to use the division algorithm for integers and write this integer as tw plus s, where s lies between 0 and is less than w. I use t and s. I'm saving q and r for a little bit later use. But s and t are integers. Everything here is an integer now. Okay, y1 prime, y2 prime came from z prime, but we chose them as integers. Now, one thing that we're not happy with, although it may not be obvious at this moment, is the range for s. We're trying to minimize a norm here, so we want to move this range so that s is centered at 0. And this is how we do it. If s is in this range, fine. Just leave this equation alone. This is valid if s is in this range. If s is bigger, it's between w over 2 and w, then we can tweak this equation a little bit by subtracting w from s, but then adding it back over here so we don't change anything. So this is just it's the same equation, just rewritten in a different way. And this portion, s minus w, now lies in this range. So if we set q to be t and r to be s, if s lies in this range, and we set q to be t plus 1 and r to be s minus w, when s lies in this range, we can rewrite succinctly that this expression is qw plus r, where absolute r is less than or equal to w over 2. And q and r are integers. Everything here is an integer. I'll just mention that one of the papers in which this is proved, I don't remember whether it's the Mathematics Magazine or the American Mathematical Monthly paper, just simply states, do this without any explanation. Okay. So, because of this, alpha can now be written x1 plus 1 over w qw plus r plus 1 over w beta. Now is the time to choose x1. Choose it to be negative q, and we get this beautiful simplification. Alpha equals 1 over w quantity r plus beta. W is bigger than or equal to 2, absolute r less than or equal to w over 2. R and W are integers. Now, one thing that might be occurring to you is, what exactly have we done? Have we just simply hidden all the complication by defining new symbols? You know, if you had, let's say, an equation that was really long and ugly, say it was equal to 0, you could say, well, let's let the left third be A, let's let the middle third be B, let's let the final third be C. Now we have a very simple equation, A plus B plus C equals 0. That has done nothing. That is not mathematics. You have hidden all of the complexity simply by defining new symbols. This is not what we have done here. It might look like it at first glance, but we made some choices for x2, y1 and y2, then x1. So the simplification is due to the choices we have made, not simply a matter of notation. So from this, we compute the norm, which is this, less than or equal to this because of the restriction of R. Now you see why we wanted R centered around 0. And that's equal to this. What now? Well, we're trying to show that delta of alpha is less than 1. We already know it's non-zero because alpha is non-zero. If W is bigger than or equal to 6, this will be less than 1. It also will be the case if W equals 5, because R is an integer, so this inequality here, this is 5 halves, but R is an integer, so we can drop this down to 4 halves, or 2. So absolute R is less than or equal to 2, and again, the numbers give us something less than 1. So we have the inequalities we are looking for, provided W is bigger than or equal to 5. Unfortunately, this approach seems to fail for W equal to 2, 3, or 4. So, I mentioned earlier that there are different approaches to this. We have to apparently abandon the approach we took here, which was to set x equal to x1 plus x2 beta and y here, and just compute. But if you go back and return attention to this expression for alpha, there's something else going on here besides setting x equal to x1 plus x2 beta, and similarly for y. If you look at this for a minute, beta is a pain in the neck. It's the square root of negative 19. But there's an easy way to eliminate it, and that is to choose y to have the form k times u minus v beta. And I'll talk about k in a minute. Because then, that's the same as this. So we needed to identify the fact that this needs to be an R, and we've got to deal with k appropriately so that this is a member of R19, excuse me. The virtue of this choice of u minus v beta is that u minus v beta times u plus v beta is u squared plus 19v squared, and beta is gone. But as I say, we have to be certain that y belongs to R19, and that will be the case. If k is an integer, then this will be an integer, and we'll have something in z plus z prime 1 minus beta, which is R19. But there's another case. If k is 1/2, this will still be in R19 provided u plus v is an integer, is even, divisible by 2. So we're actually interested in k equals 1, and that's okay, and also k equals 1/2 when u plus v is even, or in other words, when u and v have the same parity. Okay. So, as long as y belongs to R19, alpha now can be written this way. Here's our u squared plus 19v squared. Beta's gone, and we still have freedom to choose x. We got the same kind of situation we had before. We're trying to divide this expression by w. So, the division algorithm. K is going to be 1, or k is going to be 1/2 under the right circumstances that u and v have the same parity. W over k is therefore either w or 2w. So they're integers, division algorithm. Now alpha looks like this. I put here a qw over k plus r. And again, it's time to choose x, same value, negative q. We get this alpha equals kr over w. Couldn't be any simpler. And that is, in fact, less than 1 because of the range of r. So, if we choose either k equals 1, or for y, we're allowed to choose y, we're trying to choose y, or we choose y to be this value, k is 1/2, as long as u and v have the same parity, we have our inequality, the one we want. We already know this is non-zero, and so we would be, we still need to check that this is non-zero. We don't know, when we learned that, let me go back here and find this. Okay, we went all the way back here. We knew that alpha was non-zero when we chose these values. So that no longer applies. We're basically starting over here with our analysis. So we will know under these conditions that the norm is less than 1. We still have to show it's positive. Okay. Well, alpha here is equal to 0 if and only if r is 0. R is 0 if and only if either when k is 1, w divides this expression, the remainder is 0, or in this case, when k is 1/2, 2w divides this. Okay, r was the remainder in the division algorithm. So, if either w or 2w does not divide u squared plus 19v squared, and in the case of 2w not dividing it, we have to have u and v the same parity, alpha is not 0. And we are finished. Now we can look at the remaining cases. If w is 4, then this condition, u v w relatively prime, implies that u and v are not both even. If u and v have opposite parity, then we have to take k equals 1. But this expression here is congruent mod W, which is 4, to this, and this is odd because U and V have opposite parity, so it is not divisible by 4, it's not congruent to 0 mod 4. Therefore, 4, or W, does not divide this. Okay. And so alpha is not 0. And this holds. If U and V are odd, both of them, then we can use the case k equals 1/2. 2W is now 8. And we have to show 8 does not divide this. But this is congruent to this, mod 8, and this is not divisible by 8. Here is the explanation. U and V are both odd. Both of these are odd. I'm not going to go through this. I think you should pause here and see if you can do it yourself. It's just basically algebra. Okay. So in either case, this holds. If W is 3, then we have U, V, and 3 are relatively prime, and U squared plus 19V squared is congruent mod 3 to U squared plus V squared, and that too is not divisible by 3, and that's something else you should try to do for yourself, but I'll give you a hint. U can be written as 3U1 plus or minus 1, and similarly for V, and the rest should work out. Finally, if W is equal to 2, then we have UV2 relatively prime, so again U and V are not both even. If they're both odd, and you do this computation of B over A, you will find it belongs to R19, which tells us A divides B in R19, and that's false. So U and V have to have opposite parity, and a similar congruence, U squared plus 19V squared congruent to U squared plus 3V squared mod 2, this is non-zero. This is not divisible by 2, so it's not congruent to 0. And I'm going to let you verify this one as well. And that's the end. Okay, quite a lengthy proof. It looks very scary when you look at these papers, I think. But basically, I hope that you can see the path through this proof. We turned this set of inequalities into this one. And I suppose you could argue, well, it's nice to have constants here on the outside. So that's reasonable to do. But it immediately alerted us to something about B over A. We have to be careful. It's always important when you are developing a proof to think about your species. What kind of object is this? Is it a real number, a rational number, a complex number? Is it a matrix? Is it a function? And always keep these things in mind. So B over A is a different species because it doesn't belong to R19. Okay. So we investigated where it does belong, and we were able to find an expression of this form for B over A. Okay. Now we look at this alpha here, and look this way, and we have to decide what to do. Without any inspiration, one would set, okay, well, X belongs to R2, so it has this form. Y belongs to R2, it has this form. We're looking for these things, X and Y. So let's just plug in and compute. Then it takes a little bit of insight to notice that this can be, by appropriate choices of x2, y1, and y2, this can be turned into 1. And that gets us to here. And we have to deal with this. But again, we're dividing by w. That should remind us of the division algorithm. Okay. This shift of range is maybe not something you would notice right away. But if you tried to continue with this, you would find these inequalities are not working out very well. So you would back up and say, well, what can I do to make R smaller in absolute value in the hopes that the norm of alpha is less than 1? And you might think about adjusting the range here. So instead of going from 0 to w, it goes from basically from negative w over 2 to positive w over 2. Okay. When you get down to this point, you become frustrated. Well, it worked great for w bigger than or equal to 5. What do I do when w is 2, 3, or 4? Well, when you get stuck, you back up. And you move back step by step and say, is there something else I can do to improve the accuracy of my statements, my inequalities, or tweak the argument somehow? And you might end up all the way back to this expression for alpha, basically saying to yourself, well, none of what I did from this point on is helpful for those 3 cases. So what else can I do? And that's where you have to stare at this and say, I get to choose X and I get to choose Y, instead of just writing generically as arbitrary elements of R19, what else can I do? And that might be where you hit upon the idea of eliminating beta by setting Y basically to U minus V beta. Okay. And that takes you to this point here in the proof. So it's a long proof, it's a detailed proof, but there is a reasonably clear path. It's actually 2 paths through this proof to complete it.